In this lecture, we're going to be talking about three-phase full-wave rectifiers with resistive loads. So just like in the previous example for the half-wave three-phase rectifier, we're going to assume that the input voltages are balanced, meaning that they have the same peak magnitude and they're spaced out every third of a cycle from each other. So now for a full-wave rectifier, we want to make use of both the positive and the negative parts of the input voltages. And so we're going to use a bridge rectifier similar to the single-phase full-wave rectifier that we looked at. So we're going to have two diodes for each voltage source. So let's go ahead and draw the circuit for this rectifier and the input voltages to explain how this works. So just like in the half-wave rectifier example, we know that this point right here where VA and VC cross is equal to pi over 6. Now to understand what the output voltage would look like, let's follow the voltages. So we know that from 0 to pi over 6, so this part right here, we see a couple of things. VC is greater than VA, but they're both positive, and VB is negative. So the voltage right here on the anode of diode D1 is positive, and the voltage right here on the anode of diode D5 is positive, and the voltage right here is negative. Now, so what that means is that either diode D1 or D5 are on. So let's assume first that diode D5 is on because the voltage on the anode of that is greater. So remember that VC is greater than VA from 0 to pi over 6. So if that's true, then D5 looks like a short circuit, which means that the voltage right here on this node would be equal to VC. So that's connected through D5. And so if that's the case, then the voltage on the cathode of diode D1 is equal to VC. So we know that the voltage on the anode of D1 is VA and the voltage on the cathode of D1 is VC. And because VC is greater than VA, then D1 must be off. So we know for this part that D1 and D3 are off and D5 is on. Now as far as the lower portion of the circuit, we know that the voltages on the cathodes of diodes D2 and D6 are positive. So those are reverse biased, so they're going to be off. And then the voltage on the cathode of diode D4 is negative. So D4 then is going to be forward biased and it's going to be closed. Because remember that if the voltage right here is VB, which is negative, and then the voltage from VC is being fed through D5 through the output voltage and then back to the anode of D4, and that voltage is positive, so D4 must be forward biased and on. So we know that from 0 to pi over 6, diodes D4 and D5 are on. Now remember that the input voltages, we can write them down in this equation. So VA is equal to VS sine omega t, VB is equal to VS sine omega t minus 2 pi over 3, and VC is equal to VS sine omega t plus 2 pi over 3. And so we can say then that from 0 to pi over 6, since we're connecting the positive terminal to VC through diode D5 and the negative terminal of the output voltage to VB through diode D4, we know that from 0 to pi over 6, the output voltage Vout is going to be equal to VC minus VB. Because again, the positive terminal of Vout is connected to VC and the negative terminal of Vout is connected to VB. Now notice that the input voltages cross every pi over 6. So we see that it crosses right here, and then we kind of start seeing a pattern. So we can divide the horizontal axis for the input voltages every pi over 6. So here, here, and here, here, and here again. And you see that that's where they cross each other. So VC and VB cross here, then VB and VA cross, and then VC and VA cross here, and so on and so forth. And so I'm actually going to define these points right here. So every pi over 6, So this point right here will be 3 pi over 6. This right here would be 5 pi over 6. This would be 7 pi over 6, 9 pi over 6, and 11 pi over 6. And so we saw what the output voltage was from 0 to pi over 6. So now let's take a look at the next step. So from pi over 6 until 3 pi over 6. So from here to here. And then actually let's take a look at the next step as well. So from 3 pi over 6 until 5 pi over 6. So from here until here. And so we start seeing a pattern here. So VA, just going to be this bar right here, it's going to be greater than both VC and VB. However, we see that from pi over 6 until 3 pi over 6, so from here to here, VB is lower than VC. And then from 3 pi over 6 to 5 pi over 6, so this part right here, VC is lower than VB. And so remember that the voltage that we're feeding at the output is going to be equal to the greater of the input voltages. So for these two cases, VA minus the lower of the input voltages, which is going to be either VB or VC for this case. So we know then that from pi over 6 until 3 pi over 6, V out is going to be equal to VA, which is the greater, minus VB, which is the lower between VB and VC. And then from 3 pi over 6 until 5 pi over 6, V out is going to be equal to VA minus VB. And another way to look at this is we can say that from 0 to pi over 6, D4 and D5 are on. And then from pi over 6 until 3 pi over 6, D1 and D4 are on. And from 3 pi over 6 until 5 pi over 6, D1 and D6 are on. And so after that, the same thing is going to happen. So now VB is greater than both VA and VC. So the output voltage would be equal to the greatest of the input voltages, so VB, minus the lower of the input voltages, so VC, and then VA. And that's going to continue to repeat. And so we see a couple of things here. The output voltage is fluctuating every pi over 3. So these ranges right here are pi over 3. And so remember that for the half wave rectifier, the output voltage was fluctuating 3 times every cycle. So every 2 pi over 3. Because again, one cycle is 2 pi, so if it's fluctuating every third of a cycle, then it's fluctuating every 2 pi over 3. But in this case, for the full wave rectifier, it's actually fluctuating 6 times every cycle. So we saw here that the output voltage looks like this. Then the same thing is going to happen for VC. And so it's going to be VC minus VB or VA. And so we see here that we have 1, then 2, 3, 4, 5, 6 fluctuations of the output voltage every cycle. And so if you follow the output voltages, then we can say the following. From 5 pi over 6 until 7 pi over 6, V out is going to be equal to VB. So now VB is greater than VA and VC. And first it's going to be equal to VB minus VC. So that's going to be this point right here. And then from 7 pi over 6 until 9 pi over 6, V out is going to be equal to VB minus VA. And then from 9 pi over 6 until 11 pi over 6, the output voltage is going to be equal to VC minus VA. And then from 11 pi over 6 until 2 pi, V out is going to be equal to VC minus VB, just like at the beginning. And so the diodes for this case would be D3 and D6, D3 and D2, and then D5 and D2, and D5 and D4. And I actually just noticed that from 3 pi over 6 until 5 pi over 6, I wrote down V out is equal to VA minus VB, but it should actually be VA minus VC. So this right here is going to be VA minus VC. So you can kind of see a pattern here. When the A phase voltage is greater than B phase and C phase, then diode D1 is on. And then when B phase voltage is greater than A and C, diode D3 is on. And when C phase voltage is greater than A and B, D5 is on. And then when any phase voltage is on, the diodes on the bottom part of the circuit for the other two phases come on and off. So for example, when D1 is on, instead of D2 turning on, D4 and D6 come on and off. Okay, so now let's plot the output voltage and let's calculate the average of the output voltage to see how the circuit compares to the half-wave rectifier example. So I'm going to erase some things here to make some room. And so you notice a couple of things here on the graph that I've drawn. The peak of the output voltage is going to be equal to square root of 3 Vs, and the minimum is going to be equal to 1.5 Vs. And so the reason for that is that, remember that for the first portion of the wave, so from 0 to pi over 6, we said that V out was going to be equal to Vc minus Vb. And also remember that Vb is equal to Vs sine omega t minus 2 pi over 3, and that Vc is equal to Vs sine omega t plus 2 pi over 3. And so if we set V out equals Vc minus Vv, we will get that V out is equal to square root of 3 Vs sine omega t plus 3 pi over 6. And so notice there's square root of 3 in front of the Vs. So that tells us that the peak of the output voltage is going to be square root of 3 times Vs. And then we can see what the minimum of the output voltage would be by plugging in omega t equals pi over 6. Because remember, that's this point right here. And so if we plug that in, we would get that V out is equal to 1.5 Vs. So we know that V out is going to fluctuate between square root of 3 Vs and 1.5 Vs, and it's going to have a ripple that fluctuates 6 times every cycle. And so on this waveform, we can say that this part right here, just from the previous plot, this part is VAB, this is VAC, this is VBC, this is VBA, this is VCA, and this is VCB, just like at the beginning. Now, in order for us to calculate the average of the output voltage, we would have to know the equations for each one of these voltages. But that's fairly simple. We just need to subtract one phase from the other and then get an equivalent equation for that. So if we do that, we would get the following equations. Now we can calculate the average of the output voltage by, remember that the average of a waveform is equal to 1 over the period, so 1 over 2 pi times the integral of the voltage waveform over that period. And so we're going to have actually 7 integrals to solve here, because we have, if you follow the waveform here, we know that we first have VCB, then VAB, VAC, VBC, VBA, VCA, and then again VCB. So if we calculate all of those integrals, we will get the following. So you would have to plug in all these voltages in these integrals and then solve for the output. But you would get that V out, and I'm actually going to write it here at the top because I'm running out of room, but average V out would be equal to 3 times square root of 3 over pi times Vs, which is roughly equal to 1.65399 Vs. So notice that the interesting thing here is that the average of the output voltage is actually greater than any of the phase voltages. So it's greater than Vs essentially. And that's due to the fact that the output voltage is based on the phase-to-phase voltages instead of the phase-to-neutral voltages, meaning that the output voltage is not equal to VA or VB or VC, but rather the subtraction of those two, so VA minus VB or VA minus VC, and so on and so forth. So by using a full wave rectifier in a three-phase application, we can actually get a DC voltage at the output that is greater than any of the input voltages.